Hey guys, welcome back to my YouTube channel. This is Vivek. I'm studying in Information Science and Engineering, Sri Venkateshwara College of Engineering, Bengaluru. So in this video, let's discuss about on my technical seminar topic called Identification of Key Disease Under Complex Backgrounds Based on Minimalism Neural Network Architecture and Channel Reconstruction Unit under the guidance of Professor Aditya K, Department of ISC. Contents: Introduction, Related Background, Working and Implementation, Future Enhancement, Conclusion and References. So, introduction to the topic. The tea industry faces significant challenges in identifying diseases amidst complex environment backgrounds. And in this study, we propose a novel approach utilizing a minimalism neural network architecture, which is coupled with a channel reconstruction unit for accurate disease identification in a tea plants. A minimalist architecture T disease recognition model called VCRUNet based on channel reconstruction unit is proposed for a problem for accurate recognition of T disease in a complex backgrounds. And tea disease have a large influence on a tea yield and also quality, which plays a crucial role in this modern agriculture production. Manual advancement of artificial intelligence technology such as led to growing interest in investigating more precise and effective ways to diagnose tea diseases. So here in by using artificial intelligence, we can investigate more tea diseases, and traditional machine learning often extract disease features manually, which increase the complexity of disease feature extraction. So this is all about the introduction. Let's move on to the related background. So the identification of T disease under a complex backgrounds is a challenging task due to the variability in environmental conditions like leaf textures and disease manifestations. And traditional methods often struggle to accurately detect disease amidst cultured backgrounds. So, convolution-based feature fusion model, which is DCFF, this model aggregates feature information from various convolution layers into phases, thereby extending the sensory field and providing a powerful future representation capabilities. So the next one is transfer learning, which is used for a rice leaf disease recognition. An experiment showed that the Inception V3 model achieved the best performance. And the next one is residual distill transformer, which is architecture to address the issues with the identification accuracy and model interpretability in rice leaf disease diagnosis study. And the next one is spatial convolution self-attention based transform, which is SCSA transformer, which makes use of multi-head self-attention to capture feature dependencies over long distance in images of the strawberry disease. So this is all about the related background. So the next one is working and implementation. The working and implementation of VCRU net model for T disease recognition in complex backgrounds, which involves several key steps and techniques. So the first step is dataset construction, which is the first step involves constructing a dataset containing images of T diseases and also the healthy leaves. And the next step is data enhancement, which we use as strategies or employed to increase the diversity of image features and stimulating real life scenarios with variations in like lighting, angles and accurations. So the next step is model architecture, which is the VCRU net model is built around a minimalist framework consisting of vanilla net and channel reconstruction unit. And vanilla net serves as the base neural network model for feature extraction, while the CRU is integrated to reduce channel redundancy between features in the convolution neural network. Continued to the working and implementation. So the next one is transfer learning. To overcome the limitations of limited sample data, transfer learning is utilized, which is transfer learning helps to mitigate overfitting caused by the small sample size and improves the model generalization ability. So this is the use of the transfer learning. And the last one is training and evolution. Here implemented the minimalism neural network architecture and CRU model using deep learning frameworks like TensorFlow or PyTorch. The training process involves setting hyperparameters such as batch size, learning rate, and the number of training rounds. Evaluation metrics like accuracy, precision, recall, and F1 source are used to measure the model's performance in recognizing T diseases. So this is a model transfer process, which is we take a um, plant village and we construct a VCR unit and transfer the parameters to the pre-training model, which is taken in the TDC's dataset, and dataset is done the data advancement and it is sent to the training model, and which shows the obtained disease characteristics. So this study utilized transfer learning by pre-training the VCRU net model on the diverse plant village dataset. After pre-training, the model was fine-tuned on a self-built T disease dataset to adapt to the specific T disease characteristics. And here, the transfer learning allowed to model to reuse learned features and parameters, improving the performance in recognizing T diseases. And this approach helps mit, mit, mitigate overfitting and optimize the model of T disease identification, resulting in improved accuracy and efficiency compared to the traditional methods. So this is all about the model transfer process. So this is the architecture of channel reconstruction unit, which works in a three-phase split, transfer, and fuse. The channel reconstruction unit operates by implementing split, transfer, and fuse strategies to optimize feature extraction within neural networks. Initially, the input features are split to segregate relevant information, where we split to segregate the relevant information, and subsequently we transformation process is applied to extract the key features and reduce redundancy, where this transfer is applied to extract the features and reduce redundancy, and finally the refined features are fused back together to enhance the model's ability to capture the essential characteristics for accurate T disease recognition. So this is how the architecture of channel reconstruction unit works. So this is the architecture diagram of vanilla net6 network. So here we have a 6 layers, 6 features. So this specifically this architecture is suitable for the tasks like T disease identification in complex backgrounds. So the here this focus on the minimizing computational complexity and speeding up inference, and vanilla net 6 features are straightforward structure compressing stem multiple stages fully connected layers for classification. Here for classification it uses stem multiple stages and fully connected layers, and by utilizing the pooling layers, activational functions, and batch normalization to maintain essential features information while reducing the network depth, and also facilitates rapid inference, making it practical for tasks requiring fast and effective feature extraction. And this is about the vanilla net 6 architecture. So feature enhancements. Constructing a publicly available large-scale dataset of T disease to address the common issues of limited data availability in disease identification. Further, reducing the number of model parameters and computationals in future iterations to enhance the efficiency of the VCRU model net. Exploring methods to grade the degree of disease severity in tea plants during high incidence periods to improve disease management strategies. So, and continuously collecting and expanding data on common tea disease to enhance the model performance and adaptability. Investing additional technologies to improve the usefulness of VCRU net models, such as refining disease severity assessment methods and timely disease control measures. Conclusion. The VCRU net model incorporating VanillaNet and CRU offers a promising solution for accurate T disease identification in complex backgrounds. So this study emphasis on data enhancement strategies and transfer learning showcases a robust approach to overcome limitations of limited sample data. The research outcomes have a significant implications for early disease diagnosis and effectively management in tea gardens, and contributing to the long-term growth of tea industry. So this helps the tea industry to grow in a long term. And a future enhancement could focus on expanding the dataset, refining the model parameters for efficiency, and addressing challenges related to disease severity assessment and control measures. Overall, this study provides a valuable contribution to advancing tea disease recognition technology, and promoting agriculture productivity in the tea sector. So this is all about the conclusion. So these are all the references which I have taken. So please have a look to the references. Thank you.